Welcome to the video lecture on Riemann sums and definite integrals. Now recall from a previous lecture that we've talked about how to use summation notation to find the area under a curve by chopping it up into rectangles and using either left or right endpoints or something else in between, and adding up the areas of all of those rectangles and then taking the limit of that as n goes to infinity, as the number of rectangles goes to infinity, and how that turns into our exact area. So we're going to explore that a little bit more in this lecture. Suppose that we wanted to find the area of the region bounded by the curve y equals square root of x on the interval 0 to 1, and we're going to use a regular partition. So if we're going to use a regular partition, then that means each of our rectangles is going to have an equal width, and that is called delta x. So let's find this delta x first. Our delta x is going to be the length of our interval, which in this example is from 0 to 1, and we're going to chop it into n equal pieces. So this becomes 1 over n. And that means that our partition is going to look like from 0 to 1 over n, 1 over n to 2 over n, 2 over n to 3 over n, and so on all the way up until we hit 1. Now normally, just to make our life easier, we use right endpoints to construct the heights of our rectangles. So we would want to generate each of these right endpoints, and you can see that each one of them is just an additional 1 over n each time. So our right endpoints would initially start at 0, which is this initial part of our interval, and then each time to get that very first right endpoint we would have to add 1 of these widths, and then to get to the second rectangle we'd have to add 2 of these widths, and then 3 of these widths, and so forth. So each time we're going to add I of our widths 1 over n. So this becomes a nice simple formula. It just becomes I over n. So now what we do to get our actual area is we sum up the sum from 1 to n of the functions evaluated at these right endpoints. So the function at I over n, that's going to give you the height of each of our rectangles and tell you how high to go. And then we're going to multiply that height by our width, and our width is this 1 over n. So we get heights times widths, which becomes areas, and we're summing up all n of these rectangular areas. Now to turn this into the exact area, we take the limit of this as n goes to infinity. So we make these rectangles get smaller and skinnier, and that means we get more and more and more of them. And that turns this approximation into an exact value. Now to actually go ahead and figure this out, we would at this point use our function and plug in these right endpoints into that function. So we're going to actually evaluate f of I over n. Now our function is the square root function. So if we input in I over n into this function for x, then this would become square root of I over n times 1 over n. Now if you remember from our previous lecture, what we tried to do at this point was simplify this so that it would become one of those formulas that we know. We have some summation formulas for the sum of a constant, the sum of I, the sum of our squares, I squared, and the sum of our cubes, I cubed. And unfortunately, this is going to have a square root of I in it, and I do not have a formula for what the sum of the square root of I is going to be. There's no formula that exists for that. So this would be impossible for us to break down and turn into a formula and get rid of that summation. So this is going to be impossible for us to do because we don't know a formula for square root of i's. Okay? So what we're going to do is we're going to modify what we plug into our function so that what we end up with is easier to work with. And this is kind of complicated, okay? What we're going to do instead of using those typical right endpoints is we're going to say that we're going to use a partition where the right endpoint of the ith subinterval is given by x sub I equals I squared over n squared, and delta x sub I is the width of the ith subinterval. So we're no longer going to be using a regular partition. We're no longer going to have this delta x always being 1 over n. Instead, these widths are going to be changing, and our right endpoints are going to be determined by this formula I squared over n squared. So let's write out what our partition looks like so you can get an idea of what this is going to have as its partition. So the very first subinterval obviously starts at 0. And now what this is saying is that we want our first endpoint to be determined by this formula when I is 1. So if I let I be 1 into this formula, this just becomes 1 over n squared. If I let I be 2, my second subinterval is going to pick up at 1 over n squared, but now if I is 2, 2 squared becomes 4, so this is going to have a right endpoint of 4 over n squared. If I is 3, then my next subinterval picks up at 4 over n squared, and now 3 squared becomes 9 over n squared. And then if I was 4, then this would start at 9 over n squared and go up to 16 over n squared, and so on. Now if we look at the ith interval, the ith subinterval, let's see if we can come up with a formula for what this is going to look like. Now the ith subinterval is going to have as its right endpoint I squared over n squared. The one before that, or the left endpoint, is going to be what the right endpoint would have been in the previous subinterval, which would have been the I minus 1th subinterval. So this would be this formula with not I plugged in, but with 1 less than I. So plugging in I minus 1 squared over n squared. So this is what the ith subinterval would look like. I squared over n squared on the right, and I minus 1 squared over n squared on the left. So what would be the width of this delta x sub I? What would be the width of that ith subinterval? Well, its width would be whatever this distance is between these 2 points. So if I subtract them, I'm going to take the right endpoint minus the left endpoint. And this has a common denominator already, so this is just going to be I squared minus, I'm going to go ahead and FOIL out I minus 1 quantity squared. So that's I squared minus 2I plus a 1, but we have this negative in front of it, so I have to distribute that minus across. So it'll become minus I squared plus 2I minus 1. So the I squareds cancel, and this is 2I minus 1 over n squared. So this is now our delta x sub I. So a couple of major differences here. If you look at these different partitions and these subintervals, this first subinterval has as its width 1 over n squared minus 0, which would just be 1 over n squared. This subinterval here has as its width 4 over n squared minus 1 over n squared, which would be 3 over n squared. This third subinterval would have a width of 5 over n squared, since 9 minus 4 would be 5. So these widths are changing as I go throughout this whole partition. Okay, so it's not a regular partition because each one of these widths is constantly changing. Okay, the other difference is we're not just using our normal right endpoint. We have a fancy formula for how to generate each of these right endpoints. Okay, so we have our right endpoint formula. We now have a formula for what our widths are going to be. We're ready to plug it into our area limit definition of the area formula. So this is what it would turn into. The area is going to be the limit as n goes to infinity, that's what turns it into the exact area of the sum from 1 to n. These are going to generate our n different rectangles, and we want the heights of our rectangles to be determined by the function at this right endpoint. So I'm using I squared over n squared as my right endpoint formula. And then I need to multiply these by each of those widths, and they're changing. So I don't have just a nice little simple formula like 1 over n for that. I have to use this for that formula. So let's go ahead and plug that in. So instead of delta x sub I, we now know what that width is. I just subtracted my right minus my left endpoint to figure out how wide this would be. And when we simplify that, we came up with 2i minus 1 over n squared. Now what we're going to do is all that tedious work of plugging in I squared over n squared into our function and then trying to break down this summation using our formulas so that we can figure out what this limit is. Now remember what our function is. Our function is the square root function. So I'm going to take this input and I'm going to plug it in to my square root function. And the reason why we chose this particular right endpoint formula is because these are perfect squares now inside of my square root. So this actually simplifies to a nice I over n. Okay, so now what I'm going to do is I'm going to pull out some constants. This n and this n squared are independent of I. So if I combine them together, that's a 1 over n cubed, and I can pull that constant out front of my summation. What I'm left with is I times this 2i minus 1. Let me go ahead and distribute my I across. This would become 2i squared minus I. Now what I'm going to do is break this difference up into two sums. I'm going to take the sum of the 2i squared minus the sum of the I. And now I'm going to go ahead and pull the 2 out of that particular sum. So I'm going to pull this 2 out front. So what I have now is sum of I squared and sum of I. And we have formulas for those. The sum of I was n times n plus 1 over 2, and the sum of I squared was n times n plus 1 times 2n plus 1 all over 6. So I'm going to substitute in each of those formulas in for these blue boxes. And let me go ahead and take this up here, since I'm running out of room. These are long, tedious problems to do. And that's because it's a limit definition of the area. And whenever you're doing a limit definition of anything, it's always going to be long and tedious. So for this sum of I squared, I'm going to use this formula right here. So n plus 1, 2n plus 1 all over 6. And that's being multiplied by that 2. And then I'm subtracting from that the sum of I, which is that n times n plus 1 all over 2 formula. Do very minimal simplifying here. I'm going to cancel out my 2 and make this a 3. So this is n times n plus 1 over 2n plus 1 all over 3 minus n times n plus 1 over 2. And then I'm going to go ahead and distribute my n cubed across. Then we should be able to take our limits. So I'm going to leave that numerator n times n plus 1 times 2n plus 1, but the bottom becomes 3n cubed. And then when I distribute to this second fraction, the top is n times n plus 1, and the bottom is 2n cubed. Now we're ready to take our limit. Okay, so remember, n is getting really, really large, so all that we need to look at when we're finding these limits is what dominates on the top over what dominates on the bottom. So for this first fraction, we're going to have an n, and a 2n dominating in the numerator. So that's going to be like a 2n cubed. And in the bottom, we have that 3n cubed. The n cubes cancel, so this becomes 2/3. For the second fraction, we have that minus, and on top it's being dominated by that n squared, and on the bottom it's being dominated by 2n cubed. This has a higher power in the bottom, so this is going to act like 1 over 2n when you cancel out those n's. And as n goes to infinity, this is going to get large and go to infinity, which means the whole fraction goes to 0. So that second fraction just goes away. So our overall limit is 2/3, which means that the area under the curve square root of x from 0 to 1, so that would be this sort of shape right here, that area is 2/3. That's what we just found out. Okay? And this, what we saw in this example is that it's not always necessary, and sometimes it's not even possible to do it if you have subintervals of equal length. We had to modify in this example and change our partition so that it was a partition where each subinterval actually had a different width, a different size width, and we used a very special formula to make that happen and make this work out nicely. But what we're going to see throughout this whole lecture today is that it's not necessary to have subintervals of equal length. And this is what's called a Riemann sum. Okay, it's named after a very famous mathematician who helped develop all of this. It's called a Riemann sum, and what it says is if you have a function f of x defined on a closed interval a to b, let delta, that's this triangle symbol, be a partition of a to b given by a equals x sub 0 less than x sub 1, x sub 2, and so forth. So this would be like a partition where you're starting at x sub 0, then going to x1, and then x1 to x2, and then x2 to x3, and so forth. Whoops. All the way up to x sub n minus 1 up to x sub n. And x sub n is the same as b, and x sub 0 is the same as a. So that's your partition. And we're going to assume that delta x sub I, so the width of the subinterval I, is going to be this delta x sub I, and it can be any width at all. We're going to pick our c sub I to be any point in the ith subinterval. So not only left endpoints or right endpoints, you can pick any x value you want as long as it lies inside of that subinterval. Then a Riemann sum is then going to be the sum from 1 to n of f of c sub I times delta x sub I, where this c sub I is within that ith subinterval. And this is called a Riemann sum of the function f for the partition delta. So here's a picture. You can see that you've got this function f, and now we're being a lot more general. That's what a Riemann sum does. It doesn't restrict us to using a regular partition and using always right endpoints. Now a Riemann sum gives us a lot more freedom. Here, the width of the rectangles can vary. So you can see in this picture that some rectangles are wider than others. And you also get to choose your endpoints that you use. So c sub I can vary, and how we choose c sub I can vary. So in some of these rectangles, I might use left endpoints. In some of them, I might use right endpoints. In some of these rectangles, I might use a midpoint. And in some rectangles, I might use something totally different as long as it's a point within that subinterval. So you're allowed a lot more freedom in a Riemann sum because your rectangles can have different widths and your heights can be determined by different endpoints. So that's the freedom that a Riemann sum gives us. And what we're going to show is that as the number of rectangles increases, so as n increases to infinity, to make this turn into the actual area, the one restriction that we're going to require is that the width of our largest subinterval needs to approach 0 in order to get the exact area. Okay, we'll explore that more in just a little bit. So let's take a look at an example of a Riemann sum. We're going to find the Riemann sum for the function sine of x over the interval 0 to 2 pi, where the partition is x sub 0 equals 0, x sub 1 is pi over 4, x sub 2 is pi over 3, x sub 3 is pi, and x sub 4 is 2 pi. So that means our partition, to write it in a format that we're a little more used to, starts at 0, that's this point here, and then it's going to go up to pi over 4. So there's your first subinterval. Then we're going to pick up at pi over 4, and we're going to go to pi over 3. Then we're going to pick up at pi over 3 and go to pi. And then we're going to pick up at pi and go to 2 pi. So let's draw this out so you can visualize what this looks like. Here's your sine curve from 0 to 2 pi. Here's pi. So our first subinterval starts at 0 and goes to pi over 4. So our first rectangle is going to be on that little width. Then we're going to go from pi over 4 to pi over 3, which isn't very far away. So there's going to be our next rectangle. And then the next rectangle goes from pi over 3 all the way over to pi. So our next rectangle is going to be here. And then we're going to go from pi to 2 pi, so even further. So we're only going to have 4 rectangles, and you can see that they each have different widths. Now, how high should these rectangles go? That's what these c values are. So pi over 6 means we're going to go to wherever pi over 6 would be, and that's going to be how high this rectangle should be. So something like that. And then we're going to go to pi over 3, which would be the right endpoint, and we're going to draw that rectangle. Then we're going to go to 2 pi over 3, which would be right about here, and we're going to draw a rectangle that would have that height. And then we're going to go to 3 pi over 2, which would be down here, and we're going to draw that rectangle. So those 4 rectangles are the Riemann sum for this particular function using this particular partition. Okay, so let's actually compute what this approximation would be. So we're going to use, in this interval, pi over 6. Pi over 6 needs to be between these two endpoints, which it is. That's your c sub 1. Then c sub 2 was pi over 3, and that happened to be the right endpoint of this subinterval. On our third rectangle, we're going to use that height 2 pi over 3. And then on our fourth rectangle, we were going to use that 3 pi over 2 to determine our height. So this is what our Riemann sum is going to look like. It's going to be the very first rectangle, which is going to go up as high as our function goes at this pi over 6 times this width. Well, how wide is this interval 0 to pi over 4? Pi over 4 minus 0 is pi over 4. So we're going to go as high as pi over 6 on our function times the width, which was pi over 4 for that first subinterval. Now we go to our second subinterval. This time we want to use the function at pi over 3, and we want to multiply it by the width of this subinterval. How wide is it to go from pi over 4 to pi over 3? Well, you would need to subtract them. Pi over 3 minus pi over 4 is 4 pi over 12 minus 3 pi over 12, so that's pi over 12 wide. So this width of this rectangle, this little red rectangle here, has a width of pi over 12. Then our third rectangle goes as high as our function goes at 2 pi over 3. And how wide is this subinterval? Well, to go from pi over 3 to pi, if I subtract those, pi minus pi over 3 is 2 pi over 3. And then my last rectangle, I'm going to go as high as 3 pi over 2. And how wide is this subinterval? To go from pi all the way to 2 pi is a width of pi. So you can see that these four widths are all different, so it's not a regular partition, and these four inputs that I'm using are all different. They're not all right endpoints, they're not all left endpoints, they're varying. Okay, so that's what makes this a Riemann sum. The widths vary, and how you choose those inputs into your function varies as well. So to actually compute this, now we're going to use our function. We need to figure out what is f of pi over 6. Well, sine of pi over 6 is a half. So this is going to be a half times pi over 4. So that's going to give me pi over 8. Then what's f of pi over 3? Sine of pi over 3 is root 3 over 2, and we need to multiply that by pi over 12. So this is going to be root 3 pi over 24. And then our next one, what's sine of 2 pi over 3? That is also root 3 over 2. And this time we're multiplying that by 2 pi over 3, so the 2's will cancel out, giving me root 3 pi over 3. And then finally, what's sine of 3 pi over 2? That's negative 1. So when I multiply that by pi, this becomes minus pi. So I'm going to leave it to you to get your common denominators. You would change all of these to 24s, something like this, 24, then you'd get a 3 pi plus that root 3 pi plus 8 root 3 pi minus 24 pi. Combining your like terms, this is going to give you 9 root 3 pi minus 21 pi all over 24. And then those are all divisible by 3, so this would be 3 root 3 pi minus 7 pi over 8. And you can get a decimal for that as well. Okay? So that is called a Riemann sum, where each of your rectangles varies in width, and how you determine how high you go and what input you plug into your function varies as well. So, under what conditions will this freedom guarantee that we have an actual area? So, under what conditions will a Riemann sum approximate the area? If your function f is continuous and non-negative, that means it stays above the x-axis, then a Riemann sum can be used to estimate area under the graph of a function. If we choose a regular equal length subintervals partition, how can we find the actual area? Well, that's what we've already done. So here, if we have a regular partition, that means you have these delta x's, which are just b minus a divided into n equal pieces. So then our area is just the limit as n goes to infinity of the sum from 1 to n of f of c sub I times this delta x. And these c sub i's can be your choice. They could be left endpoints, right endpoints, whatever you want. And as n goes to infinity, notice that these widths, these delta x's, since we're dividing by n, b minus a is a constant, so we're going to get a constant over something infinite, and a constant over something getting larger and larger makes this go to 0. So by choosing a regular partition and letting n go to infinity, that forces these rectangles to have skinnier and skinnier widths, so those delta x's go to 0. Okay, so that's what turns it into that actual area, when you let that limit take n go to infinity, which forces your delta x to go to 0. So what if you have a partition that's irregular and n is going to infinity? So what if you have a partition where the widths are all different? Here we've got rectangles of various widths. What's going to happen? So what we notice in this picture here is that our widths, delta x sub I, varies, and the c sub i's vary. Some of them use midpoints, like this big one in the middle. Some of them use right endpoints, like this one over here. Some of them use left endpoints. So here we're using that Riemann sum idea and using different rectangles of different widths and different inputs. So this particular picture probably would not give us the exact area because we have two really big intervals here that would have a lot of inaccuracy in determining that area approximation, even though all the other ones might be really small. So as n goes to infinity, we might be stuck with some really big ones and all the rest being really, really tiny. So the really, really small ones would do an excellent job of approximating that exact area, but you'd get a lot of error from those really big ones. So we're going to need to make a restriction and require that if we're going to have a Riemann sum where the rectangles vary and the inputs vary, we need to make sure that we don't get stuck with a really large rectangle, which is going to cause some inaccuracies. So this is what we do to avoid that. So in order for a Riemann sum to approximate area, we need to require that the width of the largest subinterval of a partition delta, we're going to call that and write its notation like this. This is called the norm. Let me make it a little bit neater for you. You get these double bars, and then you put your triangle inside. That's called the norm. We need to ensure that the width of the largest subinterval, which is called the norm, goes to 0. And if it doesn't go to 0, then we're not going to get exact area using that particular partition with that particular Riemann sum. So in order for the Riemann sum to truly approximate area, we're going to require that the largest subinterval, called the norm, goes to 0. Okay, so the biggest rectangle that we see over here, its width needs to go to 0 in order for the Riemann sum to become the exact area when we take the limit as n goes to infinity. So the length of the largest subinterval of a partition is called the norm of the partition, and it's denoted by this notation right here. If every subinterval is of equal length, then that partition is regular, and we already know what the norm is going to be. The norm is just going to be that delta x, which is equal to b minus a over n. So in a regular partition, if your partition has width b minus a over n, then that's going to go to 0 as n goes to infinity, because as n gets really, really large, again, we have a constant over something big, which goes to 0. So a regular partition automatically gives us this requirement that our norm needs to go to 0. So a regular partition is good. All right, if we have a regular partition, then we're going to satisfy that requirement that our norm needs to go to 0. So that will happen if it's regular. On the other hand, if you don't have a regular partition, then the norm going to 0 is not necessarily guaranteed. So here's an example. Suppose that we create a partition, I'll call it delta sub n, where each subinterval is determined by doing 1 over 2 to the n. So if we start with the interval 0 to 1, then we would have these endpoints being 1/2, 1/4, 1/8, 1/16, 1/32, and so forth. So your partition is going to look something kind of like this. Now what is going to happen as n goes to infinity? As n goes to infinity, 1 over 2 to the n does go to 0, because this is going to be 1 over something infinite, which goes to 0. But what is our norm in this particular example? What's the width of our largest subinterval here? Our largest subinterval is this one right here. And what's its width? Its width is 1/2, which is not 0. So our little 1 over 2 to the n's do go to 0, but the norm, the largest subinterval, isn't going to 0. It's fixed at 1/2. So this is why we would have a problem using this particular partition and a Riemann sum. It wouldn't satisfy that that norm needs to go to 0, so we wouldn't necessarily get that exact area that we're looking for. Okay? All right, so now what we're going to see is how these Riemann sums relate to integration. We're going to define something called a definite integral. Now, we've already talked about something called an indefinite integral. An indefinite integral is just an antiderivative. So now we're going to talk about something called a definite integral. So here's the definition. If a function f is defined on the closed interval a to b, and the limit, as the norm goes to 0, of the sum from 1 to n of f of c sub I delta x sub I exists, then we say that f is integrable on that interval, and its limit becomes this definite integral, which has as its notation the integral from a to b of f of x dx. So this is called the definite integral of f from a to b. It looks just like an indefinite integral, except now there are bounds. A is called the lower limit of integration, and b is called the upper limit of integration. So what this formula is saying is that if you have a Riemann sum whose norm is going to 0, then in the limit, as that norm goes to 0, this will turn into the exact area represented by this definite integral from a to b of f of x dx. So we have two notations that look somewhat similar, but at this point are totally unrelated. So we now have this definite integral. For example, the integral from a to b of x squared dx. What that physically represents is the area from a to b underneath this x squared curve. So this represents the area under x squared from a to b. So it's physically an area. Okay, that's what this integral, definite integral, represents. Okay, what you're going to get for an answer, since it's an area, is just a number, whatever that size is, whatever that area happens to be. So your answer here is going to be a number for an answer. Now let's contrast that to our indefinite integral. So this would look very, very similar, but notice there's no bounds. Now the integral of x squared dx represents the antiderivative of x squared. And we know what that would be. That would just be x cubed over 3 plus c. You add 1 to the power and divide by the new power. So this is actually going to be a function, and actually it's going to be a family of functions for the answer. So here my answer is going to look like a family of functions, and it's a family because of that plus c on the end. When there's no bounds, you'll always have a plus c. When there are bounds, you're going to be getting a final number for an answer. So they're very different notations here. Very similar notations, but very different interpretations. When there's bounds, you're physically computing an area. When there's no bounds, you're actually finding an antiderivative. Okay? Now, there is going to be more of a relationship between these two things, and that's going to be something called the fundamental theorem of calculus, and that's going to show us how to relate these antiderivatives to these areas. But we're not ready to talk about that just yet, but we will. Okay, so now what we want to do is we're going to first talk about this theorem, and then we're going to practice doing some of these definite integrals. So the theorem says if a function f of x is continuous on a closed interval a to b, then the function f of x is integrable on that interval a to b. Okay, so if it's continuous, then that means we are going to be able to find its integral. So this first example says evaluate -1 to 2, the integral from -1 to 2 of x cubed dx. Now at this point, since we haven't learned this fundamental theorem of calculus yet, the only way that we can figure this out is by imagining this as an area under the x cubed graph from -1 up to 2 and finding this area. And the only way we know how to find those kinds of areas so far is by using rectangles and by using the limit definition of the area. So up to now, for now, we have to do this using the limit definition of area. So that's that long, tedious process where you find those n rectangles. You get to choose what sort of endpoints you want to use. You have to figure out your partition and your widths, and then you have to plug it all in into that limit of the sum. Okay, now we'll eventually learn a shortcut, but for now we have to use that limit definition of the area because that's all we know so far. If you remember, when we first learned about the derivative, we learned the limit definition of the derivative, which was a big, long limit process, and that took us a long while to do until we learned some shortcuts. It's the same idea here. For now, we have to use that big, long limit definition to find the area until we learn our shortcuts. So, step number 1 is to find your widths and your partitions. So our delta x is going to be this interval from -1 to 2. So take your rightmost endpoint minus your leftmost endpoint and chop it into n equal rectangles. So that means the width of our rectangles are going to be 3 over n. So our partition is going to look like this. We're going to start at that leftmost endpoint -1. And then the first right endpoint is going to be that -1 plus a width of 3 over n. Then the next subinterval picks up where that one left off, and then we're going to take that endpoint, -1 plus 3 over n, and add another width to it. So 3 over n plus 3 over n becomes 6 over n, and so on until we get to 2. So to make life easy, we've learned about these Riemann sums, but they are complicated when you have different size widths and different inputs. To make our life easy, it's just nice to use a regular partition and right endpoints, since you know that that's going to turn into the exact area once you take that limit. If you're doing a Riemann sum and you're using some crazy scheme to figure out your widths and your inputs, then you have to be careful about making sure that that norm goes to 0. So it just makes life a whole lot easier if you stick with the regular partition and use right endpoints. So what would be a formula that's going to generate each of these right endpoints? Notice the pattern here. It's -1 plus, and my width is that 3 over n, and if I multiply that by I, that will generate each of these right endpoints. When I is 1, I get this one. When I is 2, I get this one. When I is n, the n's cancel out, and -1 plus 3 will be 2, so I'll get this one. So it's always your left endpoint, -1, plus I times your width, and that will always give you your right endpoints. So now we're ready to plug it in to our limit definition. So -1 to 2, that integral, this integral is defined to be the limit as n goes to infinity of the sum from 1 to n of f of these right endpoints times the width of our rectangles, and our widths are always this 3 over n. So these are your heights, these are your widths. When you multiply them together, you get areas. We sum up all n rectangles to get all those areas, and then we take the limit of that as n goes to infinity to turn it into this exact area over here. Okay? All right, now that we have it set up, we want to use our function. And what's our function? Our function is this function inside of our integral, our x cubed. So I am going to substitute in this right endpoint into the x cubed function. So this is going to become negative 1 plus 3I over n quantity cubed times 3 over n. So now at this point we're going to need to do some simplifying. Take that regular width, that partition width, and pull it out. It doesn't have an I in it, so we're allowed to pull it out of our sum. And then I'm going to have to do this nasty work of cubing out this negative 1 plus 3I over n quantity cubed. If you do that, you're going to get a negative 1 cubed, which stays negative 1. You're going to get 3 times negative 1 squared times 3i over n, which becomes 9I over n. Then you're going to get a minus 3 times negative 1 times 3I over n quantity squared. So that's going to be 27I squared over n squared. And then we're going to get a 3I over n quantity cubed, which is 27I cubed over n cubed. So if you don't trust me on that, you can go ahead and cube this all out. But this is what you would end up with. Okay? All right. Now what we want to do is split up these 4 terms into 4 different sums. So the sum of the negative 1. This 9 over n, I'm going to go ahead and pull it out front of my sum. So I'll just have the I in there, minus this 27 over n squared. I'm going to go ahead and pull that out front of my sum. So I'll have just the sum of I squared. And then over here I'm going to pull out my 27n cubed. And that'll leave me with the sum of I cubed. Now we have formulas for this, 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 and this. So I'm going to substitute in all of those formulas, and these are formulas that we learned in a previous lecture. So leave that 3 over n where it is. The sum of a constant is just that constant times n. So this is going to be negative 1 times n, or negative n. Then the sum of I is n times n plus 1 over 2. Then we have that 27 over n squared times the sum of I squared. That's the n times n plus 1 times 2n plus 1 all over 6, plus the sum of cubes formula was n squared, n plus 1 quantity squared all over 4. Okay, so the next thing that I'm going to do is distribute this 3 over n across to each of these 4 terms. And again, I'm not going to do very much simplifying. I'm going to try and let the limit do most of the simplifying, or at least as much work as I can make it do. So if I take 3 over n times a negative n, the n's cancel out and I'm just going to get a negative 3. If I take a 3 over n times the second fraction, on top we're going to get 3 times 9, which is 27, and I'm also going to have my n and my n plus 1 still there. And in the denominator I'm going to have an n times a 2, which is a 2n squared. And if I take 3 over n times the third fraction, 3 times 27 gives me 81. And then I'm going to have my n plus 1, and my 2n plus 1 still there. And in the denominator, n times n squared times 6 gives me 6n cubed. And then for my fourth fraction, 3 over n times 27 is going to give me again another 81. And I'm going to have my n squared, n plus 1 quantity squared. And then the denominator, an n times an n cubed is an n to the fourth. So we'll have a 4n to the fourth. Okay, so now we're going to actually take our limits here. If we take the limit of a constant, which is what this first term here is, we just get that constant right back again. So this first term just stays negative 3. In the second fraction here, remember that when you take limits going to infinity, what you're looking at is what dominates on the top over what dominates on the bottom. So if we look at this second fraction, in the numerator, we're going to get an n times an n. So this numerator is going to be dominated by 27 and then an n squared on top. And then in the denominator, we have a 2n squared. And the n squared over the n squared is going to cancel each other out. So this whole fraction is going to be dominated by those ratio of coefficients, 27 over 2. In the third fraction, we're going to get this negative 81 still out front. And then in terms of the dominant terms, we've got an n, we've got an n, and we've got a 2n. So that's going to be a 2n cubed. And 81 times 2 is going to be 162. In the denominator, we have that 6n cubed. So the n cubes cancel, and we're just going to be left with the 6, and there's a minus in front of all that. Finally, for our last fraction, we have our 81 out front, an n squared here, and then this n plus 1 quantity squared is going to be dominated by another n squared. So in total, we'll have an n to the fourth in the numerator, and in the denominator, we have that 4n to the fourth. So the n to the fourths cancel, and we're going to be left with 81 over 4. So when we get to this point, you just pull out your calculator, you punch it all in, and what you end up with is a total value of 3.75 or 3 3/4. So let's remember what this number here that we just figured out represents. This 3 3/4 represents the area under our curve, which was x cubed, from x equals -1 up to x equals to 2. And if you visualize this on a graph, x cubed looks kind of like this, -1 would be about here, and +2 would be over here. So we're talking about this shaded area right here. And in fact, when we notice this, we've got some of our area below the x-axis and some of our area above the x-axis. So this integral right here, this amount that we just calculated, this is actually called signed area. And that's because any area that's below the x-axis is going to be considered negative area, and any area above the x-axis is going to be considered positive area. So when you combine the two and you add these two areas together, in this case we have slightly more positive area than we have negative area, and that's why our final answer ended up being a positive net amount. So our net area was positive in this case. So signed area represents the area below the x-axis as well as above the x-axis, and anything below is considered negative, any area above is considered positive. All right, so that whole process of doing that limit definition of the area, that's very tedious to do, but sometimes, at this point, that's all we have available to us. On these next examples, we're going to see if we can find a few shortcuts to help cut down on a little bit of that work. Now for these first two here, all we're going to do is set up an integral that would yield the area shown in the region. So here we have the line 4 minus 2x, and we want to show, or we want to find the integral that represents this shaded triangular region. So the integral, definite integral, is going to be the integral of the function that you're trying to find the area of. So that would be just this 4 minus 2x. The problem is we don't know what bounds to use. So we either need to look at our picture, which it's kind of hard to see the scale on there, or we need to figure out what those bounds should be. And obviously this first bound is going to be 0 because I'm starting at that y-intercept. But the question is, what is this intercept over here? Well, that's just going to be where my line, 4 minus 2x, hits 0. So if you solve that, divide by 2, that's going to tell you that this hits at 2. So my bounds need to be from 0 to 2 of 4 minus 2x dx. So that's what the integral would be for that particular area. Okay, well, what if we want the tangent function, and it's, again, hard to see the scale here, but this is going by ones, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. This last one over here is 0.8. It's hard to see that on the graph. And we're starting over here at 0. So the bounds that I want are from 0 to 0.8. The function that I'm integrating underneath is that tangent function, and for notation purposes you always include that dx if you're using an integral. So there's my integral. That's it. For number 5 here, we want to sketch the region whose area is indicated by this definite integral and then use a geometric formula to evaluate the integral. So let's sketch this first. The function that we're using is this x over 2. So the function that we're really using, if you want to rewrite this, is 1/2 x. That's just a line. It has a y-intercept of 0 and a slope of 1/2. So we go up 1 over 2. So it's going to look like that. And we're doing this from 0 up to 4. So from 0 to 4. So the area between 0 and 4 is just this triangle. So what's the area of that triangle? We don't need to bother with doing that whole limit definition of the sum and chopping this up into rectangles, because this is an actual triangle and we have a nice simple geometric formula that calculates the area of a triangle. It's just 1/2 base times height. So let's just use that instead, and then we'll be able to figure out this area exactly. So what's the base? The base would be this width going across here, which is just 4. And what's the height? Well, that isn't quite so obvious, but remember, this line is 1/2 x. So if we're looking at this when x is 4, 1/2 of 4 means this is at a height of 2. So this height is 2. My 2's cancel, so my area is just 4, which means this integral is just 4. So we were able to calculate the value of this integral without doing that whole limit definition of the area, because we ended up with a nice geometric shape and we already had a formula for that shape. All right, let's try the integral from -a to a of the function a minus absolute value of x dx, and we're going to assume here that a is positive. Okay, so what does the graph of a minus absolute value of x look like? Well, first of all, an absolute value graph is just a big V. When you throw that minus in there, that flips it over, so it's going to be a V upside down. And when you add that a in front, that's a vertical shift. So when x is 0 here, this is going to hit at a. And this is going to be a big V just like this. And when x is positive a or negative a, then you'll end up with a minus a, which is 0. So that's why the two x-intercepts are at a and negative a. So if we're looking at the integral from negative a to positive a of this curve, that means we're talking about this area right here, which again is just another triangle. So we can use the area of a triangle formula to figure it out. Now you can do this a couple ways. You can do the area of this full triangle and do 1/2 base times height. The base of the entire triangle all the way across this base, I go a to the right and a to the left, so that whole base would be 2a. And what's this height here? That height is also a. So when I do that multiplication, the 2's cancel and a times a is a squared. A second option would be to just find the area of one of these triangles, 1/2 base times height, so 1/2 a times a, and then there's 2 of them to make the full area, so when you double that, that 1/2 cancels out. So no matter how you do it, you're going to get that this area is just a squared. Okay, how about the integral from -2 to 2 of the square root of 4 minus x squared? Now think about that function for a moment. That would be like y equals square root of 4 minus x squared. Now you may not know what that is when you graph it, but look at what happens if I square both sides. and if I add that x squared to the other side. This should be an equation of something you're familiar with. That's a circle centered at the origin with a radius of 4. But if you work your way backwards, when you take the square root of both sides, you should really be getting a plus or minus square root when you solve for y, and this is only using the positive square root. So what that means is that this graph isn't the full circle, it's just the top half of the circle where we're using the positive y values. So this is a circle with a radius of 2, so this is going to hit at 2 and negative 2, and it's going to hit up here at 2, and we're just using the top half because this is an implied positive square root. If I had a plus or minus symbol in there, then I would also have the bottom half as well. But we only have the plus. So what would be the area from negative 2 to positive 2 under this top half of the circle? Well, it's just that area right there, which is a semicircle. So how do you find the area of a semicircle? Well, area of a circle is pi r squared, so area of a semicircle would be 1/2 that. And what's our radius? Our radius is 2, so if we plug that in, we'll get 1/2 of pi times 4. Half of 4 is 2, so this is just 2 pi. So this area is just 2 pi. Okay, now let's talk about some properties of definite integrals. This one says that the integral from a to a of f of x dx is equal to 0. And you can kind of visualize that because if you think about just a function f from a to a, that means we're not going out to the right or to the left at all. So there's no area because there's no width at all. So that's why this integral would just be 0. So if your top and your bottom bound match, then that area will just be 0. The next one here says the integral from a to b, so that area right there, is the same as negative the integral from b to a. So there's kind of a direction involved here. If I integrate from a to b, I'm going to get the answer that I would get going from b to a, but opposite sign. Okay? So if you switch the bounds of integration around, you have to flip the sign out front. That's what this one is saying. Okay, the next example here says the integral from a to b is the same as the integral from a to c plus the integral from c to b. So this one, again, is very geometric. It's saying that the area from a to b, that whole integral, that whole area, can be thought of as the area from a to c plus the area from c to b. So we just pick this point C in between A and B, and we can chop up that full area into 2 smaller pieces. And if we add those 2 smaller pieces together, we'll still get the full area. So that's what this property 3 is saying. Property 4 says the integral from a to b of a constant times a function is the constant times the integral of that function. So this is kind of like our constant multiplier rule. You're allowed to pull that constant out front if you want. The next one here says the integral of a sum or a difference is the sum or a difference of our integrals. And that's just like the rules we've had for derivatives and limits in the past. And then the last one here says if you have a function f that is less than or equal to g of x on an integral, then the area from a to b under f should be less than or equal to the area under g from a to b. So again, this is very visual. If you think about a function f, which is lower than some function g, then from a to b, the area under f, which is this red stuff, is obviously going to be less than the area under g, which would be the blue stuff. So that's what that property is saying. All right, so let's use some of our properties here. Given that the integral from -1 to 1 of f is 0, and the integral from 0 to 1 of f is 5, find the integral from -1 to 0 of f. Okay, so this is going to be that property number 3 that we're going to use. We're going to kind of take one full interval and we're going to chop it up into 2 smaller pieces. So out of these 3 intervals, -1 to 1, 0 to 1, and -1 to 0, the biggest interval is the -1 to 1. So -1 to 1 of f of x dx could be chopped up into -1 to 0 of f of x dx plus the integral from 0 to 1 of f of x dx. So all we're doing is we're taking this function and we're taking this whole area from -1 to 1 and we're chopping it up into this piece plus this piece. So that's what that property allows us to do. Now we know that this integral, they tell me, is 0. This is the one we're trying to find. So I'm going to leave that the way it is. And this one, they tell me, is 5. So if I subtract that 5 over to the other side, then that means the integral from -1 to 0 of f of x dx is just going to be -5. Okay? All right, how about the integral from 0 to 1 of f of x dx minus the integral from -1 to 0 of f of x dx? Well, the integral from 0 to 1, they told me, was 5. So this is 5. And we want to subtract from that the integral from -1 to 0, which we just figured out was -5. So this is -5. So 5 minus a -5 becomes 10. Okay, how about the integral from -1 to 1 of 2f of x plus 3 dx? So here we're going to use some properties of integrals to split up this sum, and then we're also going to use some constant multiplier rules. So first I'm going to split up this sum into the integral of 2f of x dx plus the integral of 3 dx. So I just split up the sum. Now this 2 is a constant multiplier, so I'm going to pull it out front. And you could do the same with this 3, but I'm just going to leave it in. And this, they told us at the beginning, was 0. So this goes to 0. So 2 times 0 will just be 0. And this one we can figure out geometrically because this represents the area under the curve f of x equals to 3. Well, what kind of function is always 3? That's a horizontal line, the constant function. And this is asking for the area under that from -1 up to +1. And what shape is that? That's just a rectangle. It's a rectangle that has an area of length times width, and its length going across here would be 2, and its width going up here would be that 3. So its area is just 6, which means this integral is just 6 because the integral represents the area. So this final answer is just 6. Okay? And then this last one here, we want the integral from 1 to 0 of 2f of x dx. So the first thing I'm going to do is I'm going to pull that 2 out front. And then if we look back at what we know the integral from 0 to 1. We don't know the integral from 1 to 0, but we have this property up here that says if you switch the bounds of integration around, you take the opposite sign out front. So if I want the integral from 1 to 0, I can switch the bounds and change it to 0 to 1, but in order to do that switch, I need to put a minus out front. And this, they told me, was 5. So when I multiply that by my -2, that is now out front, this just becomes -10. Okay? Next example. Express this limit as a definite integral. So this should look like a Riemann sum. This is the limit, as the norm goes to 0 of the sum from 1 to n of 3 over c sub I squared delta x sub I. So out of all of this, we need to try and figure out what integral this represents. So first of all, one easy thing that should be able to be determined are the bounds, because they tell me what interval I'm looking at. So those are your bounds right away. This has to be from 1 to 3. The next thing we need to figure out is what function it is that we're using here. And remember, for your Riemann sum, you're taking the sum of those f of c sub i's times those delta x sub i's. These are your heights of your rectangles. These are your widths. So what function is it that we're using if, after I plug in c sub I get 3 over c sub I squared? What must my function f of x be? Well, it's got to be 3 over x squared. So that if I plug in c sub I for x, this becomes 3 over c sub I squared. So the function that we want to use and the function that we want to integrate is just 3 over x squared. And then this delta x sub I turns into, now you can kind of see where this notation comes from, turns into that dx that we always write when we're doing our integral notation. So that delta x sub I, which is that width, is just your dx in your integral notation. So our final answer here, the limit definition of the area is the definite integral from 1 to 3 of 3 over x squared dx. Okay, the last example here. Assume that the region below is bounded by semicircles and straight lines. Find the value of the indicated definite integrals and which integrals can be interpreted as areas. Okay, so we're actually going to interpret all of these integrals as areas. So let's take a look at this first one. We want the integral from -2 to 1 of this function. So -2 is right here, and 1 would be right here. So the integral from -2 to 1 means the area underneath this graph all the way up until we get to 1. So that's just a semicircle plus a triangle. So if we can find the area of those two shapes using our geometric formulas, then we'll know what this integral happens to represent. So area of a semicircle is 1/2 pi r squared. Now what's the radius of this semicircle? Its radius is 1. So this is going to be 1/2 pi times 1 squared. Plus the area of the triangle is 1/2 base times height. My base here is 1. And my height up here is 2. So if I simplify, I'm just going to get pi over 2 for that area of the semicircle, and 1/2 times 2 cancels out to just a 1. So this area is just pi over 2 plus a 1. Okay? All right, now let's do that again. But this time we want the integral from 10 to 3 of f of x dx. Now that should kind of bother you a little bit because you don't want the bigger number on the bottom bound and the smaller number on the top. We like to go in order from left to right. So the very first thing I'm going to do is I'm going to switch these bounds around. So I have the smaller number on the bottom, the bigger number on the top. But in order to do that switch, we need to counterbalance with a negative. So this integral here now represents the area starting at 3 and going all the way to 10. So that's going to be all of this area right here plus all of this area. Now remember, this is signed area, which means anything below the x-axis is going to be negative. Anything above the x-axis is going to be considered positive area. So we're going to add in this sort of trapezoid shape, and then we're going to subtract that semicircle area. Okay, so what's the area of a trapezoid? Area of a trapezoid is 1/2 the height times base 1 plus base 2. So we want 1/2 the height. The height is this height right here, which is 2. Base 1, I'll pick to be this bottom base, and that's from 3 up to 6, so that's a distance of 3. And base 2 would be this top base up here, which is from 3 to 4, so that's a width of 1. So these 2's are going to cancel out, and 3 plus 1 is 4, so the area of that trapezoid is 4 units. Now let's go to our semicircle. Area of a semicircle is 1/2 pi r squared, and our radius here is this distance from 8 to 10, which is a distance of 2. So we want 1/2 pi times 2 squared. 2 squared is 4, half of 4 is 2, so this will be 2 pi. We want to subtract it because it's lying below the x-axis. So this total area, signed area, is going to be 4 minus 2 pi. Okay, next example. Now we want the integral from -4 to 0 of this function. So that's going to look like -4, which is right here, all the way to 0, which is here. So we want this area, and that's below the x-axis, so we want to count that as negative, plus this area, which is above the x-axis, so it's going to be positive. So we want our negative triangular area plus our semicircular area. So we want minus 1/2 base times height. My base here is this distance, and that's a distance of 2 units, times my height, which is this height here, and that goes down to 2, so that height is 2. So half of 2, those cancel, so this is going to be -2. Then we want to add to that our semicircle, which is 1/2 pi times the r squared, and my r here is 1. So this will be 1 squared. So this is going to be plus 1/2 pi. And there's our area. Okay, the very last one, the integral from 3 to 8 of f of x dx. So if I color that part in, from 3 to 8, so here's 3 to 8. So I'm going all of this minus this. This is negative, this is plus. Oops, so I want my trapezoid minus, now this is no longer a semicircle, it's going to be a quarter circle. So the trapezoid, we already did that over here. That was 1/2 the height, which was 2, times base 1, which was 3, plus base 2, which was 1. That was this 4 that we got earlier in part B. And this time we're just going to subtract not a half circle, but a quarter circle. So 1/4 of pi r squared, and my radius here is 2. 2 squared is 4, 1/4 of 4 is 1, so this is just going to be pi. So my final area is 4 minus pi. All right, that concludes our lecture on Riemann sums and definite integrals. Good luck.